security for IoT.
All right, thanks for the introduction. It's my pleasure to be here, and I have to say I'm really proud of each and everybody who's still here after 4 days of conference in the Netherlands on a Friday evening. So I'm really, really happy that still a few people showed up. As you just mentioned, I'm working at Dark Matter, and I'm running the hardware lab there. So we do everything from hardware hacking to sidechain and fault injection, and also invasive attacks, microprobing, reverse engineering, all the nice toys we play around with, and we do some research. We just started last year, so everything is still in the ramp-up phase, and we are constantly expanding. But this is not what my talk is about. So my talk is about something completely non-technical. It's more much more abstract point of view. And the reason is 5 years ago, when I pivoted from academia to industry, I was repeatedly stunned by the decision taken by management that had an impact on product security. It doesn't mean that the product is insecure, but it could have been more secure each and every time they made the decision. And I was wondering, why is that? Why does it happen? And what are the mechanisms at play? And so this talk is really just a collection of thoughts that I collected over the last 5 years. I try to back it up with data as much as possible, just to make it a bit scientific, but that fails. And some of the statements, I couldn't find data. And you just have to either believe me, or maybe I overlooked something. So I'm happy to have a discussion afterwards. It could be also plain wrong. But I think this is just my take on it, and why we have these issues in IoT security in particular. And so in the next 35 minutes or so, I'd like to follow this outline, quick motivation. Then I would like to pinpoint like 4 root causes that I believe are at the core of the issue. Are not easy to fix, and they're still a few layers away from daily work, but still I think that's the root causes. Then I would like to have a closer look on the security trade-offs. And then eventually, what should we do? What should we as a community do in our different capacities to trying to make this a safer place? And finally, a quick conclusion. So I think you have all seen the headlines this week that Tesla key fob was hacked. And for me, that was stunning for many reasons. One is that this is one of the most expensive gadgets that you can buy for $70,000 roughly onwards. Probably some of the best engineers build it. And it's probably one of the most sophisticated cars that there is, with all the software updating and all these things. So security is probably good thanks to Key Labs and others. But this is, yet it could be hacked for $600 worth of equipment within 2 seconds. And that's actually worse than state-of-the-art. State-of-the-art are relay attacks that you can pull off with $20 worth of equipment since a few years, repeatedly, and so on. So that's not even the best part of it. So typically relay attacks, you can only start a car once and drive away. But then you cannot start it again because you don't have the key fob and it's out of range and so on. What they did is they completely broke the cryptographic scheme. So I thought that is dead, but apparently still there's bad crypto out. And that means they can completely clone the key fob, and then they can drive the car and start it whenever they want. So what they did is, and this is really stunning to me, in the key fob used in this Tesla, in this flagship model of Tesla, a proprietary 40-bit cipher was used. And that is already twice bad, because it's proprietary and 40-bit and not 128 or 256-bit, but it's really bad. And what's even worse, and that's why we have this small thing at the bottom here, it was already broken in 2005 and published. So, and when I thought this is a great addition to my introduction to this talk, it's why in 2018 would a car be hacked with a cipher used by one of the best engineers in the best cars that is broken since 30 years. How does it happen that a cipher like this ends up in a product like this? And this is pretty much what I'd like to have a look at in the remainder of this talk. So why is it that there's this mismatch between state-of-the-art in research and what ends up in products? And thanks to a well-known IoT security advisory company, I found the top 10 IoT vulnerabilities. And if you have a look at it, it's also not rocket science, right? It's hard-coded sensitive information, meaning keys, seeds, and so on, initialization vectors. Enabled hardware debug ports are still on. You have insecure firmware, insecure data storage, insufficient authentications, insecure communication, insecure configuration, insufficient data input filtration, insecure mobile interface, and finally insecure cloud and web interfaces. So this is not rocket science. This is known to be done. It's hard sometimes, but people know how to do it. So why is it still the top 10 of the IT security? So where does this mismatch come from? From state-of-the-art research and knowledge how to do things, and then eventually the product level that ends up for in particular IT devices. So that's what I'd like to discuss in the next couple of minutes. Maybe I should move over here. So I think one of the root causes is that it's a complex product, IoT, and that means you have a combined attack surfaces. It's not rocket science either. So you have some kind of data generating device in the field, low cost, embedded with all the constraints. So you have all the embedded security attack vectors with physical attacks, fault injection, power, invasive, memory dumping, and cost constraints. And then some of the data are sent into the cloud. So that's network security attack vector that needs to be taken care of. And finally, the data is somehow used. You want to monetize it. So there's analytics running around it. So you have all the APIs that have another attack surface. So that, I think, is one of the main reasons why it's so insecure. And product complexity also means division of labor. So if you look at the ecosystem of IoT, this is unfortunately a bit outdated, 2016, but you can see it's a lot of different companies that do a different share of the product. You have a hardware manufacturer, maybe a firmware producer, maybe an operating system on top. You have someone for the cloud and the server and the analytics taken care of. And all these things need to work together. And this complexity is also very difficult to get secure. This is one of the data points I couldn't update because I couldn't find a more accurate or more up-to-date quote. It's still my feeling that IoT is strongly influenced by startups. So 4 years ago, there was a statement from Gartner, which is a market research firm, that predicted by end of 2017, 50% of all IoT services will be made by startups that are less than 3 years old. I don't know if it's 50%, and I don't know if it's less than 3 years old or not, but the point is still a vast share of the IoT products are produced by startup companies. And what does it mean? I mean, some of you are entrepreneurs, some of you work in startup companies, you know the pressure. It's from 0 to 1 within a few years. You need to get office space, you need to hire people, you need a tax invoice, legal stuff, the product needs to be going, you need a POC going to get the next round of venture capital funding. And yeah, the product needs to be good, but time to market is mostly crucial. And if you look at, I found this bar of priorities for products, and you can see here that the most important metric for many of these who took part in that how do you call it, questionnaire, many of the companies said speed to market is most crucial. And then the second one is cost minimization. And then you have user experience, that is usability. And then you have quality, feature completeness, and yes, somewhere here between unimportant and desirable, you have security. Because it's a trade-off that goes against all the others. So if you want to maximize speed to market and minimize cost, you don't want to maximize security. That's typically counterproductive. And yeah, in the end, the implications for IT security are if you have a startup-dominated landscape and all the huge attack surface and cost constraints and everything, then it means there's a lack of focus because you need to get your bills paid, you need to get the next round of venture capital, you need to get people hired. There's lack of expertise probably because people wouldn't hire a security engineer rather than a software engineer or a product designer, and time to market is most crucial. Then the question is, Tesla is not a startup anymore. Why did they still do it? Why do big corporations like Tesla, Volkswagen, and other who have the means, who have the manpower, who have the money, who pretty much also have the time actually to implement that, why do they still fail with security again and again and again? And I think here it's very important to notice that corporations are risk averse. The moment companies are financially driven, they have to report every 3 months their financial figures, and they have to be within their prediction corridor of revenue. They shouldn't outperform, they shouldn't underperform, should be exactly in how analysts predicted their performance. So they need to be reliable, dependable, non-risky. So all the decisions from CEO down trickle down to be risk averse. And that typically happens in companies. And I think the reason why this has an implication on security is, and that's actually the major reason why we can't have better security, is that security is hard to quantify. What is security? When is a product secure? When is it secure enough? How much more security do I get? How do you measure that? How do I compare that? So that's a real reason that you can't quantify security, from my point of view. And yeah, so if we assume then, this is a shitty curve, sorry, that I try to make asymptotically. I think you can see it. So what I wanted to depict here is that if you have one of the trade-offs, time, cost, usability or unusability in this direction, and unperformance in that direction, I wanted to say when you invest the first few bits of time or unusability, you get a lot of security gain. But after a certain period of time, if you want to make it more secure, you need to invest a lot of more of time and effort and unusability and unperformance to even get it a bit better. I think that's known. So if you look at military grade security and what they invest, then you're probably here. For IoT, probably you want to end up somewhere here, because you can never be 100% secure. So, but then if you can't quantify security, how do you know where you are? If it's just hunches and feelings and guesses, everybody has a different understanding where you would be on this curve. And that makes decision difficult. If the CEO comes or some decision maker and says, we need to show or ship the product in 2 months, and then the engineer says, no, I need 2 months to make the security better, then we need to delay it by 2 months, then the natural question is, if I delay by 2 months, how much more security do I get? Is it worth the investment? If I need $2 million more to make it secure, how much more security do I get for that? Is it worth it? Yes or no? It's the investment and the return on investment. And you can't quantify that if you don't know where you are here. And let's have 2 quick examples. If you believe you're here or we are here, and you say, yeah, let's do 2 more months, $2 more million of security, then yeah, you get this much of gain here. And yeah, probably it's worth it. But how do you know? We can't say. So on the contrary, if you're already here and you want to do the same investment, then what about these gains? They're probably not worth it. And management typically tends to believe you're here. They believe marketing. And the engineers, they typically tend to be here. So they always want to over-engineer. And since you can't quantify it, time is a binary measure. It's either on time or not. Money is a binary measure. It's either more or less than what you predicted. Security you can't predict. So it's really hard to get that discussion and the decision process in favor of security. Now let's have a closer look on these 4 trade-offs: time, cost, usability, and performance, and how they influence security. Okay. So it's time to market. I think it's most crucial for most companies because they need to beat their competitors to the market. And the challenge is always when you do a security assessment, when are no findings a good thing? So when someone says, I need 10 seconds to draw a Batman, and you get this, yeah, it's a Batman. Someone says, I need 10 minutes, and then you get this one. If you relate that to security findings, after 10 days you have only this amount of findings because you only looked at this attack surface, and after 10, let's say, weeks or month, you have a much clearer picture of the attack surface. At what point of time it's good to say no security findings is a good thing? In particular for side channel or other hacking, if you can't break it, it doesn't mean it's secure. It could mean that you're not good enough to break it or that something is wrong in your methodology. So at what point of time is it enough? And it's really hard to make that when you can't really quantify the security level. You can't say it, sell it to management. And the question is always, how much more do we get when we spend more time on this? And you can't sell it. So then for cost, I think the most important is here that cost of a breach is hard to estimate because these are the real costs of the lack of security. But it's really hard to estimate upfront what's the likelihood and how much would it cost and how bad is the breach and so on. So it's really hard to say the savings of security by investing more in it. And I wanted to put an example here using 2 very old pictures of microcontrollers, secure microcontrollers. I took them from this paper from Ross Anderson and others from 2006. It's 2 microcontrollers. And on the left-hand side, you can clearly see every IP block clearly identifiable. So Olivier Thomas would probably like that and would know exactly where to go and where to dig in. On the right-hand side is a chip where everything is meshed into glue logic. So all these individual components, they are synthesized together and meshed together. So I wanted also to use that not only to discuss the costs, but also the benefits of obfuscation here. So if you look at the left-hand side, what are the benefits to have clearly identifiable IP blocks? So you can optimize them. If you have a hard macro in hardware, you can hand optimize them to be low power, low area, low delay, and high security. And you can test them as much as you want, unless you're sure they're secure. And then you just reuse that same hard macro in different derivatives, and you can be pretty much sure it will have the same security as initial testing. So in the end, you get a high performance, low cost library of IP components, and that can be a very big advantage. On the other hand, when you have glue logic, every time you do a synthesis run, it will be assembled to different standard cell libraries, and that means the leakage characteristic, for example, for sidechain is different. And it also means that it could be probably sometimes compilers optimize away countermeasures because the random mask that is actorized here and here doesn't need anything. They just remove it. This all happens. So all these things could happen. So each and every time you have a new derivative, you need to do the full security assessment again, and you can't optimize as badly or as good as you do here one time because it doesn't pay off over different derivatives. So in the end, it's less performant, hopefully as secure, because that should be the same, but it's less performant and it's much more expensive and takes more time to deliver products with the glue logic. But what are the drawbacks of this approach? Once an attacker, first he can easily find the interesting spots, the crypto coprocessors, the buses, the memory access points, and these kind of things. So you know where to go on the one device. But even worse, once one of these devices is broken, because an attacker now knows where to put the sidechannel probe or where to shoot with a laser, he can break the exact same IP core with the same attack on different derivatives. So it's like a monoculture versus a diversified bio ecosystem. But yet again, the question is each and every time then, for each and every time you use a glue logic, how much more security do we gain? It's hard to quantify, but the gut feeling would say, let's go for it. It's a nice extra layer of security. And in this sense, the obfuscation here is on top of everything else that you do. You do your homework with security assessment, everything, but on top of that, you make the extra effort to make it harder for a reverse engineer to get to the points where he gets information he needs to carry out an attack. And if you wonder why I put this picture of wood here, anyone notice what's in there? No? No? Not even you in the front?
It's a road.
Say again?
It's a road behind it?
No. So this is there's an asset hiding in plain sight, an asset for a lion. So there's a giraffe here. If you look at it, there's a giraffe. Here's the nose, eyes, ears, standing here in plain sight, but it's really hard to find it. Right? So even there's no security between her and the lion, that is the first measure of protection. Usability. This is the first trade-off that is also very soft and not binary. What is usable? What is good usability? How much pain basically will our users accept to use the phone? The product. And one question could be, how much pain do they have to accept to make it secure? That's an engineer wants to make it very secure, so it's pretty much hardly usable. So a good example, coming back to the Tesla hack, is if you would have something like this. I don't know this device in English, but it's a nice low-cost analog device, low power, everything, right? And on top of that, it sends a message. It's not easy to hack in here. It's a deterrent. So that's a really nice thing. But no one has it anymore. It turns out people don't want that. And the real question is, how much pain will the users accept? And how much do they want to accept? And they don't want it. They want it Face ID. They want walking through without any hassle of authentication. And that's the same for cars. So 20 years ago, they came up with passive keyless entry and start systems. And that means you just go to the car, open it, press a button, and go away. Because your key fob is constantly... once it's in a proximity, you authenticate it because the key fob is in a proximity. But again, didn't take long to figure out you just can use relay attacks, and I think everybody has seen this video. guys here with a signal boosting device, because typically the keys, when you come home, you put the key next to the door. Everybody does that. So they have a booster device here. The second guy is a receiver and relays the signal to the car, which believes the key fob is there. You can start and drive away. And that's something, it can only be addressed by distance bounding protocols, which are still not rolled out, may come or not. And this attack actually, or this usability trade-off, has led to the fact that car thefts have been risen. In Germany, there are some cars where the insurance premiums have doubled because the companies say it's stolen too often, and it's because you have this feature. So there's some market mechanism at place now, because at some point, if people don't buy it anymore because it's too expensive, then there might be but it's, from a technical point of view, it's very hard to get this user feature, make it secure. And what is Tesla's response? They introduced pin to drive security feature. So we're pretty much back to square one, only in a digital world. You have to enter a pin, and that's probably a hassle if it's a long pin. So, but that's exactly the trade-off between usability and security. And typically, people want a usable device, and security should be an afterthought. But it's really difficult to trade off here. Yeah. Finally, performance. It's area, memory, clock cycles, power, battery time, and so on. And we saw this nice talk by Helena today regarding side channels. If you do performance optimizations without taking security into account, you always have side channels enabled. And I'd also like to quickly recall the square multiply for RSA. As Helena already mentioned, the private key is exponent. On an embedded device, you typically go bit by bit. You scan it bit by bit. When it's a 0, you do a squaring. If it's a 1, you do square and multiply. And this way you can go through the bits, and if you can distinguish a squaring and a multiplication, you can read out the bit from the power trace. Plus, the timing is dependent on the numbers of ones. So if you have 50% ones, then there should be 50 multiplications, 50%. 50%, okay. Let's put it differently. If you have 10 bits, 5 are ones, you have 5 multiplications. If it's all ones, you have 10 multiplications. So the difference is clearly visible in time. So one of the countermeasure is a square and always multiply. So you always make a dummy multiplication. But that immediately means that you always end up with the worst case performance in a computer science sense. And that's the same for power and area and everything else. If you optimize really for the low power, and only that crypto component is consuming power at the time when it's doing it, it's very good for the attacker because it's a very clear signal. So that it's a trade-off between performance and security. It's also another example for performance over security is the return of the coppersmith attack. I don't know if you're familiar. Last year there was this big problem in some TPMs, I think 50% of the TPMs, when the smart card library that generated the RSA, that generated the primes that were used to generate the RSA key, there was a weakness. And that is because the library that was used was super performant, but unfortunately the primes it generated were a bit weak. So I'm sure they put it there because they believed it's secure, but I think a really big drawing card for that implementation was that it was so efficient and so fast. And unfortunately, performance and security is sometimes really difficult to balance. Also, something that Helena mentioned earlier is that in this new super secure, and we should all buy it from Rambus, the CMRT, there is no caches in there. And that's the next question. Are we willing to get rid of caches in for the sake of security? And what about Spectrum Meltdown and Foreshadow? Are we okay with 20% less, 40% less, 50% less performance? Are we willing to get rid of all these benefits that we have earned over the last 20 years only for the sake of security? That's a tough discussion. And again, it's easy to argue the performance loss. It's very hard to get the security gain unless you can show that certain attacks are not valid anymore. So what should we do? What we as a community should do in our different capacities? So this is not rocket science. What I'm saying is just a few thoughts again, what I think what could help address these problems. So for hardware hackers or researchers, so many in the room here, I think it's really important to continue responsible disclosure despite all the negative hate and heat and beef that you get. It creates pressures for companies to react. And typically inside the company, you have people who are happy that this happens. So they have a case for management to say, see, I told you, I wanted to have this extra week of assessment or security, and they couldn't get it. So it really creates pressure for the company to react. It also clarifies somehow the cost for the lack of security, which helps in future product discussions. And if you do it for all manufacturers of a certain product, it also creates transparency. If you don't focus on a single ledger device, for example, then it creates transparency about the security level in the market. I think it's important that you try to understand the constraints of the engineers or the companies. There's the PR and the CEO and the management kind of things who want to reduce the risk for the company, so they downplay your attack and they ridicule you and so on. But then also the engineers who are really trying to fix this. Maybe they don't know it. Maybe they don't have the power to get the decisions through because of the mechanisms I was just saying. And I think for hardware it's really important to think that sometimes you can't fix it in hardware. I heard a talk from a guy from, I forgot his name, it's a professor in UC San Diego. He was basically the first guy who hacked cars back in 2010. It was 4 years before Charlie Miller and everything else that were out in the press. And he said they hacked a lot of things and they didn't disclose it because companies couldn't fix it. So it's up to you to decide whether if you disclose it and cannot be fixed, if it makes the world better or worse. Because if they had pushed it out, people could have been killed remotely because the things couldn't be fixed at that time. And I think that's a tough decision to make, but I think it helps to be more open to the arguments of the engineers. Hey, believe me, we need 1 year to fix a new generation of chips, or 2 years. You need to wait a bit, and so on. So I think it's important to try at least to understand the constraints. And I also like all the open source tools, but I would also like to say it's not enough to just put it on GitHub, maybe with some comments. Think if you want to make an impact and make it more secure, you need to aim for the noobs, for the engineers who have the job of fixing it and that don't know how to do it. Not for the experts. The experts are the bad guys. They know how to use it. So they are happy for your tools. But the guy who has to fix it, they don't know how to do it. So it's always good to have tutorials, examples, videos, and how-tos. Or obviously a consulting gig with them maybe afterwards. Because typically what people do in companies, they look up these tutorials, and if they need more information, then they reach out to the authors and are willing to pay. So it could be some kind of advertisement for you as well. Then if you look at engineers, then I think the most important is to always ask the manager for independent security reviews. It doesn't need to be an external company. It could be an internal penetration testing team, but it needs to be independent. And the money and time writing costs and everything needs to be factored in. It could be low cost. You could just go to a university and ask a professor to put a bunch of students on it. That's even better than nothing. Or you can ask one of the many freelancers that are out there that give all these trainings and so on. Or one of the labs that are out there could also be asked. I think it's really important that there's no first time right. And I think you need at least 2 iteration of reviews. At least, the more the better, but let's don't stretch it. So put out your design, get the review, get the feedback how to improve it, get another review and improve it again. And I think that's already a very good cycle. And you have 3 development cycles. Then you should have taken out the low-hanging fruits and made it much more secure. But that's not always easy to justify. Once we had a situation where we had like 5 or 6 iterations within 2 weeks, and I was super proud reporting to my manager, we've done this in 5 to 6 iterations, now it's good. Why does it take 6 iterations to make it secure? He thought it's bad, they couldn't do their job on the first time. No, it's a good thing that they, I really went down to the last 3% now. And yeah. I think this is really important. Findings are not criticism on your work. It's constructive feedback. I don't know who had this, but for me, we had a situation where we had some theoretical findings and we wrote a report, and the feedback was, this is Mickey Mouse, James Bond science fiction stuff. You can't pull it off. So obviously we did some proof of concepts and wrote a report and didn't believe it. So then we took some videos and sent them over, and then they said the video's fake. So, so how to deal with that? I mean, it was for me a challenging situation to keep my temper, but in the end I tried to understand their point of view, and I think it boils down that they believe that we said your baby is ugly, but it's not. It's what we said is your baby is beautiful and you want to protect it, and if you let it walk through, it goes in front of the bus, and we want to help them be more mature in that sense. So I think this is really important. And still, whenever you get a review on your work, it feels like someone's criticizing your work, but it's positive and constructive feedback. I think it's important to educate yourself using all these amazing online resources, and hopefully all the noobs videos and examples that will be there. And then once a certain level is reached, then it's really valuable to sign up for the trainings to get the most out of it, because the trainings are not cheap, but I guess they're worth it. And to get the maximum out of it, you need a minimum level of understanding. For managers and decision makers, I think it's crucial for every product to have a security architect who has two roles or two responsibilities. One is that he owns the security, so it can be chopped. He can take the blame and everything if the product fails, but you can't do that if you don't control the budget and the timelines. If you separate that and one person is responsible for the time and money and all the other typical KPIs for a project, and another person is responsible for security, it will never work, because security is contrary to all the other KPIs. This guy will always minimize or maximize his KPIs, and which is always contrary to security, and it always has friction. So this person needs to be responsible for both, and then there's a chance that it works. You need budget for security reviews and improvements, and I mean not only for external companies, but also the time writing costs and so on. And then there should be time for 3 iterations, as I mentioned. It needs to be clear that it's not first time right, but it's a good thing to have an iterative cycle. And I think it's also important to accept the fact that the product is not unhackable. We've seen it again and again. No matter who claims it, products will be hacked sooner or later, and companies should be prepared for it with bug bounty or PCERT. I heard that some companies do this now, a PCERT program. And I think this is also most important, that the researchers should be rewarded and not seen as enemies, because they do a great job in finding flaws and bring it to your attention, and you can fix it. You can engage with them. You pay them money because they did a great job up front. So all the risk was on them. They deliver results, and you don't have to take the risk. They took the risk because they invested their time up front. For academia, I think it's important to think about how to quantify security. What is a good way to get a comparable measurement for security? And how to quantify in particular the extra gain of security versus the other trade-offs. If I invest 2 more weeks, how much do I get more? At least some guidelines how to do that. How to compare security of different products, I think, is really important to get transparency, so that the consumer has an incentive to buy better products. If you can't compare, everybody claims hardware security, but trust zone is something different from a secure element. Both say it's hardware security, but it's different. And what's the level? And it's really hard for a customer to make the decision. How to measure the strengths of obfuscation? I think obfuscation is a good add-on once you have done your due diligence and Kirchhoff's principle and all the security, everything that you've done on top. You can do some obfuscation to make the life harder for people to get access to your data. And then obviously the soft problems. So how to incentivize companies to invest in security, how to incentivize customers to pay for security, and also the bug fixes, because the products need firmware updates, it's really expensive. So how do you incentivize it? Who's going to invest that money? Who is going to benefit? And finally also secure third-party components, in particular in automotive. You have a lot of black box components that come in. You have this huge supplier trees, and typically it works that the OEM specifies a functionality to the tier 1 supplier. He says, okay, I deliver to that. The tier 1 takes that, breaks it down to further specifications, and brings it down to the next level of tier 2, tier 3 suppliers. And then they only deliver a black box, so you can't have any access to the source code or anything to see if it's secure or not. It's just what you specified. And that's by design, so you can have competitive bidding and all this stuff. But how do you do to deal with that for security? Alright, then conclusion. I think there is no secure product. It's just where the management or the decision makers settle on any of the various trade-off points. It's a compromise between performance, usability, time, cost, and security. It's always a compromise, but it's crucial to get clarity if that point is really reached. If you don't know where you are, your risk management is wrong. So how do you know if that is really reached? So you need independent assessment. Again, internally or students or freelancers or labs or whatever, you need, the more the better. The more you invest in that clarity, the better is your understanding of security level. And then again, I think obfuscation on top of this well done homeworks can make attacks very hard in practice. If you think about the Tesla hack, the cipher was broken in 2005, and yet only in 2018 it was discovered that it was in the Tesla key fob. And researchers had to reverse engineer to figure that out. So maybe there was a smart decision from Tesla to go with that, because no one saw the giraffe in plain sight because it was hidden. So, but I think since obfuscation plays for practical product security an increasing role, also reverse engineering is increasingly important. So getting that pulled back and getting some strength mechanisms from this last layer of defense is really important. It's not understood, as far as I can say. All right, that's it. Thank you very much.
Who's going to ask the first question?
You.
I just wanted to say, first of all, thank you very much for the talk. One thing I've heard here, which I've not heard in a similar venue before, is the pros of obfuscation. Usually, obfuscation is the enemy,
Yeah,
and it tends to enable the attackers more than the good guys.
I agree. I think this is probably the most contradicting statement of me in this venue as well. But if you look at Twitter, how people complain that they can't access to the data sheets of secure elements, and that it's really hard now to hack this device. Exactly. That's why you don't get access to the data sheets. So, but this only works if it's not security by obscurity. But if you have, and for smart cards, you do have this very heavy overhead evaluation and certification process that ensures that there's a decent security level with all the JHAS level 31 points and all this stuff. And then on top of that, you take away all information that you can. You control the samples. People can't get access to the devices. They can't get access to open devices. Precisely for that means, so that they can't tamper around and get smart for their attack. And I think that's one of the reasons why I think obfuscation on top of everything can be very helpful, because smart cards are really rarely hacked. From my point of view, they are typically the strongest part of the system. It's just a few smart card hacks, but typically it's somewhere else in the system where it's hacked.
I think we don't have any other questions. Thank you.
Thank you.